Welcome everyone to FusionEPtalks. This is a student-led webinar on fusion science and technology. My name is Daniel Medina, and it gives me immense pleasure to introduce today's speaker, Cyd Cowley. Cyd is a third-year PhD student at the University of York, part of the UK Fusion CDT program. He completed his undergraduate at the Imperial College London, where he published work on dust tracking in tokamaks. He is now working on projects at York, CCFE and MIT, mostly focused on plasma modeling for advanced divertor. So without further delay, I will hand it over to Cyd for you to start your talk.
All right, thank you very much, Daniel, for the great introduction. And yeah, thank you, FusionEPtalks, for hosting me and allowing me to speak today. So as Daniel said, my name is Cyd. I'm a PhD student at the University of York, also working for the Cullum Center of Fusion Energy and MIT. I want to talk today on advanced divertors, a cutting edge tool to control plasma exhaust. And that was a little bit of a joke there. Since I work on edge plasma physics. So what I wanted to do today was give pretty much an overview of advanced divertors, what they are, why we care about them, why I'm researching them, and then go a little bit into what my research is contributing to this field in particular. And really, at the end of the day, it all boils down to nuclear fusion. So achieving sort of sustained economical nuclear fusion, man-made nuclear fusion reactors here on Earth would really represent a revolution in our energy supply. And that's because fusion represents a potentially safe, low carbon, highly available, and virtually inexhaustible supply of energy. And more these days, this is a revolution that we really seem to need, particularly when it comes to climate change and when it comes to energy independence, being independent from oil and gas and geopolitics when it comes to energy. And so one of the key ways in which we're trying to achieve nuclear fusion on Earth is through machines known as tokamaks, as you can see in this figure here. So the purpose of a tokamak is it's this sort of toroidal or donut-shaped device, which has these colloidal and toroidal field coils, as you can see here, generating toroidal and colloidal magnetic fields. These magnetic fields confine and stabilize a roughly 150 million degree burning fusion plasma. And this is essentially, the idea of a tokamak is to contain, because nuclear fusion happens, in all the stars in our sky pretty much, and in our sun. That's where it gets all of its energy from. But the sun has the advantage of having massive gravitational fields to stabilize and confine your fusion fuel. We don't have that on Earth, and so we use magnets instead in these tokamak machines. Now, one key challenge when it comes to operating with tokamaks is that occasionally you'll have some hot plasma escape the core and have to touch the surrounding material that we make our machine out of. You can clearly see, the issue here. We have 150 million degree burning plasma, 10 times hotter than the actual sun, and some of that escapes and touches a man-made material. And so we need to, control and make sure this process is as gentle as possible when the plasma interacts with our surrounding materials. And one of the ways in which we've controlled this in the past is using divertors. So typically what we do in tokamaks is we use magnetic fields, colloidal magnetic fields. And colloidal is the sort of, when I mention the colloidal direction, I mentioned this cross section of the donut here, whereas toroidal sort of goes around the donut like this. And so we use colloidal field structures to literally divert the plasma escaping radially from this core and divert it towards these strong heat resistant target plates that you can see in blue here. So that's one way we've had in the past of managing our plasma material interactions. And the benefit of operating in a diverter configuration is we can have the plasma material interactions happen physically far away from the core by diverting the plasma and creating this solve or scrape off layer. This can lead to lower target temperatures, but it can also keep the core nice and pure and free of materials sort of coming off the surface and entering the core. So where are we in terms of tokamak research right now? Well, right now we're operating with very scientific devices. They're not at the stage where they're power plants yet. But the sort of next generation of devices that we're building, so we're currently operating with devices such as JET, the Joint European Torus, which you may have seen in the news recently. But the next generation of devices will be either reactor-like or reactor tokamaks. And when we go to this sort of next stage of tokamak development, one of two things or both of two things are going to happen. We're either going to aim for a larger machine with more energy coming out, or we're going to aim for better confinement through higher magnetic fields, for example. Both of these are bad for plasma exhaust, because if we have a larger machine, the energy density sort of increases massively, but the area that it's spread over doesn't necessarily increase that much. Similarly, with better confinement, the area that all of this power coming off the core gets spread over gets smaller and smaller and smaller with better confinement. And so for these next generation devices, there's going to be massive heat and plasma fluxes towards these plasma facing components. And in fact, for ITER and demo, the unmitigated fluxes would be way too much for even the strongest materials to handle. And so for future devices, we've got this sort of exhaust challenge or exhaust problem, where we essentially have to drop temperatures by a factor, heat fluxes and temperatures by roughly a factor 5 to anywhere between 5 and 100 from here to there. So, in this sort of, 1 meter space colloidally or a few meters space colloidally, we have to go from, we have to drop temperatures and heat fluxes by, possibly factors of nearing 100. So this is a significant challenge, and a lot of people are working on some great edge plasma physics to find out how we can do that in future devices. And one of the main ways that we can do that is by operating in a mode known as detachment. And detachment is a mode of operation where what we can do in these machines is we can inject some sort of impurity, such as nitrogen, which can radiate a lot of power in the plasma. And so what happens is we can actually radiate most of the power that the plasma is carrying before it reaches those material targets. You can see an example of that happening here in the compass tokamak. The benefit of this is that if we radiate most of the power before the plasma actually reaches the target, then what we get is quite literally a high temperature, high energy plasma detaching from our target, leaving a sort of cold, nice and cold region of a partially ionized gas from that radiation front to the target. And so because, we get nice and gentle heat loads at the target, and because we're radiating a lot of the power away, it's a lot more evenly spread. And because of that, we generally get better plasma material interactions and sort of less violent interactions at the target. You can see that here in the compass tokamak, that when we inject nitrogen, you can see at the start, the divertor targets are literally red hot. They're incredibly hot. And that redness is essentially indicates how hot the targets are. But when we inject nitrogen, it forms this blue radiation front. It sort of detaches from the target, and those targets cool down. You stop seeing that sort of really red hot radiation. And as I said, one way of achieving detachment is by injecting some impurity, such as nitrogen, which radiates the power away. But there are actually a few different ways of achieving a detached state. You can increase just the plasma density, which also increases your power losses. And you can decrease the power of the machine, which essentially decreases the amount of power that you need to lose before you get to a detached state. And so by changing essentially your impurity concentration, your upstream density, or your heat flux entering the diverter, you can get closer or farther away to a detached state. And so we call these three sort of numbers detachment control parameters. The issue with these control parameters, though, is we don't actually want to increase them or decrease them too much. For example, if we increase our impurity injection, we might actually affect core stability and radiate too much of the core power away. If we decrease our power too much, we can decrease the efficiency of the core machine. And so really, what we want to do is have detachment be as easy as possible to get to. We don't want to have to inject tons of impurities. We don't want to have to decrease the power of the machine. We want detachment to be easily achievable in machines. And so how do we do that? How do we make it easier to achieve? And this really is one of the fundamentals behind advanced divertors. So advanced divertors are a way of getting closer to a detached state. They're a way of reducing power and particle loads on these targets just by changing the magnetic configuration, the shape of your divertor. You can see a few examples of advanced divertors in this figure here, and you can see, they have very different shapes of their colloidal field structure. And the idea is they leverage different types of physics to get us close to that detached state, to reduce power and particle loads on our targets. How do they do that? Well, they leverage a load of different types of physics. And what I'm going to do now is sort of take you through the menagerie of different divertors that we have in our arsenal and what they sort of leverage. And let's start with a very important parameter to leverage, which is the connection length, or the parallel length a particle has to travel from the upstream, so from either the outer midplane where all of that power is coming out of, or from the X point where the power gets sort of concentrated. The length that a particle has to travel from the X point to the target, right? So it's the length between your hot, dense core and your target, your material target. And so what certain advanced divertors try to do is they try to get longer connection lengths. How do they do that? Well, you can see one of the key divertors that tries to do that is called the X divertor. And you can see that here compared to a conventional divertor. And you might be saying, well, okay, you want to increase the connection length, but this doesn't actually look that much longer. The lines, you know, from the X point to the target here, doesn't actually look that much longer in the X divertor case. And indeed, you'd be right. But that's not necessarily how the X divertor increases connection length. What it does is it lowers the poloidal field in this region here. And what that essentially does is it doesn't change the length in the poloidal plane in this cross section that we're viewing it, but it means that particles have to travel more toroidally. They have to spin more around the donut before they hit their target. So by lowering poloidal fields, we can increase connection lengths of divertors, and that's what an X divertor does. Here's a little GIF to show you what I mean. When a particle goes from the core to the target, it's not just traveling, you know, in the poloidal plane, it's whizzing round as well. And when we decrease the poloidal field, we make it whiz round more for a given step in that cross section. What is the benefit of a longer connection length? Well, it essentially acts like insulation between the core and the target. It means that we can have a higher temperature difference between upstream near the hot dense core and downstream near the target. So either for the same target parameters, we can have a better upstream temperature, a higher upstream temperature, or for the same upstream temperature, we can get lower target temperatures. A knock-on benefit of this is that for the same target temperature, so if we're trying to achieve the same level of detachment, for example, longer divertors have higher upstream temperatures, and because that they have higher average pressures in the divertor, and this can lead to actually more radiation. So longer leg divertors can actually radiate more and get you closer to detachment. Another key feature that advanced divertors try to leverage is what's called total flux expansion. And essentially, what these divertors try to do is they take the target location to a high major radii. So in the poloidal plane, that means at a high sort of value on the x-axis here. You can see the target sort of horizontally shifted to the right. And what this does is, because magnetic field depends on major radius in these machines, this means we have a lower magnetic field at the target, or a high what's called total flux expansion between the X point and the target. Why does this matter? Well, the heat, when it comes to a divertor plasma, is sort of spread on the parallel area of what's called these magnetic sort of flux tubes. And when you decrease the magnetic field strength, you make those flux tubes sort of wider, and you increase that parallel area. So for the same heat coming in, we're spreading it essentially over a larger area. So we're decreasing the heat flux density, the sort of power per meter squared. And so lower magnetic fields have, in general, lower heat flux densities, or regions where there's lower magnetic fields, we have lower heat flux densities. And so, you know, when divertors have high flux expansions, they have low heat flux densities at the target, and that gets us closer to detachment, right? Divertors that implement this include, for example, the Super X divertor, which you can see here. The reason it's called Super X is it also has the poloidal, the low poloidal field, the poloidal flaring that we see with an X divertor, but it also has this flux expansion taking out to a high major radius. So it's a combination of an X divertor and this effect. Finally, not finally, but in addition to that, we can also add multiple X points in our plasma domain. So here you can see an example of a snowflake divertor, which implements this multiple X point phenomenon. What does this allow us to do? Well, this decreases the poloidal field in the region where we have our X points, which again increases connection length, we like. But what it can also do is introduce more legs, more divertor legs, and have more power sharing throughout those legs. So I hope you can see that if we only had this first X point here, we would only have 2 divertor legs. But because we have 2 X points in the domain, we have 4 divertor legs, and the power can be sort of shared over multiple legs. So snowflakes use these multiple X points. We can also have just double nulls, where you can essentially just have any configuration, make it vertically symmetric, and that can share power loads over the top legs and the bottom legs. Finally, I'd just like to talk about quite a new recently proposed configuration called the X-point target. And this is sort of a greatest hits advanced diverter, if you like. It implements pretty much everything I've talked about so far into one nice, neat diverter geometry. So it has two X points in the plasma domain, one here and then one near the target, shown in red. And what this does, but the target is also at a high major radius, so it has high flux expansion. Because it has that second X point, it has pollutal flaring and so a high connection length. And you also have power sharing due to the second X point here. You can see this leg sort of splits into two, so you have power sharing as well. So it kind of is a mishmash of all those features that I've talked about. So this is sort of a summary of different advanced diverters and their concepts. But where's sort of research now when it comes to advanced diverters? Well, if we think about it with regards to complexity, a lot of great work is done on the more theoretical side, and that's what we use to design these advanced diverters, are concepts, 0 and 1D models to help us sort of think about this intuitively. And then on the other side, we have world-class experimental devices such as Mass Upgrade, TCV, D3D, which can implement advanced diverter configurations and study them. We also have really complex 2 or 3D simulations for these advanced diverters. But what we don't have as of yet is a lot of in between, a lot that's bridging the gap between this theory and this complexity. And what I mean by that, for example, is in experiment, what you can do is you can compare a conventional versus a super X diverter, for example. But what is difficult to do in experiment is determine, okay, if a super X diverter is better, if it achieves detachment easier, why is that? What feature is it? Is it the pollutal flaring near the target? Is it the high flux expansion? Is it perhaps the physical baffling of the wall? And it's hard to sort of separate which isolated feature is making the difference. And so what I try to do in my PhD project is try to understand, okay, what features we think are important when it comes to fundamental understanding, are they important when we add physical complexity to the problem? And the work so far that I've done has tried to do this with two tools. The first is what's called the Detachment Location Sensitivity Model, or the DLS model. It's essentially a 1D model for heat balance in a diverter along one given flux tube. And it essentially assumes that your diverter looks like this when it's detached. That you have your heat flux coming in, it only varies due to magnetic field up here, and then it completely goes away at one location, which we call the radiation front or detachment front, and it goes away because your impurities that you've injected have radiated all of that power away. And so this is what it assumes a detached diverter looks like. And when you work through the math of solving this heat balance, you can actually get an expression that relates your control parameters. So, what densities and impurity fractions you need to be in a given detached state. It relates those to advanced diverter features. So it relates those to flux expansion, connection length, and the other great things that we talked about. And that's sort of more on the theoretical understanding side. But what we've also done is try and confirm or deny a lot of the predictions made by that simple model with more complicated simulations. So we've used SOLPS-ITER simulations, and SOLPS-ITER is a simulation architecture that's a combination of a plasma fluid code and a kinetic Monte Carlo code for kinetic neutrals. It's got a lot of physical complexity in it. It's a really great code. But in the past, it's just been used to study, real configurations. And what we've tried to do in this study is use these isolated diverter legs, as you can see in this figure here. The benefit of this is, again, we remove some of that complexity. We try to bridge that gap like I was talking about earlier. And we can change in these isolated diverter legs, we can change 1 or 2 geometric features at a time. So we can really study not just is the conventional better than the X-point target or whatever, but we can ask the question, is this feature better than this other feature, right? And I think that's important for developing our understanding for how to design diverters. So one thing we looked at is the access to detachment, how easy it is to get to detachment. And the DLS model predicts that essentially this parameter CT just tells you how easy it is to get to detachment. It tells you what densities, impurity fractions, and powers you need to get to a detached state. So the higher it is, the harder it is to get to a detached state. The lower it is, the easier. So we generally want CT to be lower. Here you can see it's related to the magnetic configuration of your diverter in the DLS model through three basic terms: connection length, flux expansion, as we talked about earlier, and then this term, the average diverter average magnetic field, which I'm not going to talk about today. But what we did was we made these SOLPS simulations of isolated diverter legs to test what is the importance of each of these features. Is it actually what the DLS model predicts? And so we did that for connection length, for example. We ran simulations of boxes of different lengths, identical in every other way, but with different connection lengths. And the DLS model said that on the y-axis here is how easy it is to get to detachment, so lower better. The DLS model says that that detachment access should vary with the connection length to the -2/7, as you can see here in red. We get a similar relationship when we run our simulations, but it is indeed stronger than theory suggests. So you get a bigger difference in detachment access when you change the connection length than theory suggests. Similarly, we ran simulations looking at flux expansion. So we take identical boxes and we rotate them so that the target magnetic field is different in every case. So we get higher and higher flux expansion going from 4 to 1. Now, the relationship predicted by the DLS model is this sort of linear relationship between ease of detachment access and flux expansion to the -1. We do indeed get pretty much a linear relationship, but again, it's stronger than expected. Going from grids 4 to 1, the detachment threshold varies by a factor of 2.3. So it's 2.3 times easier for case II1 to be detached than it is for the 4 grid. Which is very different from the 1.7 predicted by the DLS model. So as well as looking at just access to detachment, we can use the DLS model to predict how detachment evolves. So when we have this radiation front, how it moves with regards to a change in, for example, when you eject more impurities, your radiation front can move further and further away from the target, and the diverter can get more and more detached. But we wanted to look about how that movement changes in different diverter configurations. And we can do that using what's called the detachment location sensitivity in the DLS model. And that just tells us how far a radiation front, a detachment front will move given some change in your control parameters. So if you increase impurity injection by 2%, will detachment change by a lot or a little? Will the front move a great deal or not? And regions of high sensitivity mean that it moves very suddenly, and low sensitivity means it moves quite slowly with respect to changes in the plasma. And one important prediction made by the DLS model is that where there are magnetic field gradients, parallel magnetic field gradients, we should get slower movement, relative movement in front position. So what we did to test this out was we ran detachment evolution scans, increasing our impurity injection to get more and more detached. And we did that for a vertical grid where there's 0 magnetic field gradient going from the target to the X point, because we're not changing our major radius, and that's really what changes your magnetic field. And then we do it with a horizontal grid, and this does have a magnetic field gradient because we're moving through a major radius as we go from the target end here to the X point there. And theoretically, the DLS model says that the movement should be slower in the horizontal case. Indeed, that is what we find. If you look at this curve here, these simulation results are in black for the vertical and green for the horizontal. And for when we increase our impurity or our control parameter by 20% above what it was on the threshold of detachment, you can see that the vertical leg moves twice as far as the horizontal leg, right? The horizontal leg moves about 0.1 meters, the detachment front, whereas the vertical leg about 0.2. We also predict that poloidal flaring has an effect on this detachment evolution. And in particular, the DLS model says that in regions of poloidal flaring, that low poloidal field, when those field lines become farther apart, the detachment fronts should move slowly through those regions. Indeed, we run SOLPS simulations, and that is indeed what you see. Just visually, you can see that the vertical grid for the same sort of changes in control parameter moves a lot faster through the first 0.2 meters than the flared grid, which is exactly sort of what the DLS model had expected. In fact, we calculated, near the target, it's about 5 times slower movement in the poloidal case. One final thing I'd like to talk about when it comes to the work I've done so far is the fact that the DLS model predicts that when we have grids with negative magnetic field gradient, and that means where the target magnetic field is greater than what we have at the X point. So in a grid like this, which is sort of it's an inner leg rather than an outer leg, so it extends, this way rather than that way, if you see what I mean. In these grids, we should actually get different detached solutions depending on whether we increase our control parameter or decrease it. So if we start attached and increase our impurity injection, we should get different solutions to if we start very detached and start decreasing our impurity injection. And so we asked, does this actually happen in simulation? And indeed, we see that when we're increasing our impurity seeding, these are the sort of results that we get. But when we start to decrease our impurity injection, we see that we can operate with the same control parameter. And when we were increasing our control parameter, we were attached. And when we're decreasing it, we're detached to 3 meters off the target. So very, very different solutions for the same control parameters. And that's just because it depends on what path you sort of take to access these solutions, which we think is quite an interesting conclusion. And as you can see here, here's the different paths that you take going forward or going backwards. And you see this backwards region here would be attached if you were going forwards. It should be at 0, but when you go backwards, it's not, or the front should be at 0. Right, so this is just a quick, webinar summary of advanced divertors, why they might be important for magnetic confinement fusion, and what sort of my PhD in particular is trying to contribute to the field. I really hope you've enjoyed, and yeah, if you have any questions or you'd like to start a discussion, I'd be very happy to. Yeah, thank you.
Thank you very much, Cyd, for a very interesting talk. Maybe as I don't see any questions, I will start asking one myself. So yeah, I have to say that I also did an internship in Compass doing nitrogen seeding to achieve the detachment, and now that I'm doing my PhD in impurity transport, I think maybe it's not very related to your topic, but I am thinking about how could the impurities, I mean material coming from the wall, be taken into account in these models, because I am very interested also in the heat load in the divertor, especially during ELMs, and I have found that there are physical ways that impurities are pushed by the plasma to the edge, and those could be also useful to achieve detachment and to radiate the power. But maybe just a basic question: how are these impurities also taken into account in these codes, and also when it comes to injecting neon or argon or other gases to achieve detachment?
Great question. So in the simpler model, so in the detachment location sensitivity model, we assume that essentially all we assume about impurities is that we have an average fraction, which means it always scales with your electron density. It's like 3% of your electron density or whatever. And we don't assume anything about how that impurity radiates with regards to temperature, apart from the fact that it's thin and not outside the bounds of your upstream and your downstream temperature. This obviously is not really true for impurities such as argon or neon, where they actually have a very wide sort of range of temperatures at which they radiate, and some of them can be greater than maybe what your upstream temperature is, or can extend into they can radiate not just in the divertor region but towards the X point and higher. And so what we've done on that, on the modeling side, is we've also developed a more numerical version of this model, where rather than assuming anything about your radiator, you still assume an average concentration, but you can input whatever cooling function you want. So you can model argon a bit better, and things like that. With the SOLPS simulations, to try and match better, we just inputted a fixed fraction as well. But you can, of course, do these simulations, and the normal thing to do with these simulations is have full impurity transport models. So have carbon wall and carbon coming off it, or nitrogen literal seeding, and it isn't injected uniformly everywhere. So I think that's really one of the next big steps in understanding this is, okay, we kind of understand, I think, better where we have some constant impurity in there. But what happens, how do advanced divertors affect impurity transport? You know, that's another thing to consider. And they do a lot. And I think it's interesting to sort of try and fundamentally understand, yes, you know, or hand wavily understand, you know, how my horizontal grids have different impurity transport than vertical grids, or how my, you know, things like that. So.
Okay. Thank you very much. We have a question from, well, two questions. First is Guido.
Okay. Yeah, sorry. So I have a question. So what are the technical challenges of installing such advanced diverters in a machine like demo, for instance?
It's a very good question. Yeah, so what I haven't highlighted here, and I guess, okay, there are two main things I'd like to highlight about advanced diverters that I haven't talked about already. One is when you change things like colloidal flaring and total flux expansion, you also change how your field lines intersect with your material. And I haven't really covered that, and that's an important feature when it comes to advanced diverter, but also one that's limited by your engineering. Another thing I haven't talked about is the cost or difficulty of implementing these. So when it comes to things like your super X diverter and total flux expansion, these are generally expensive things to do, because what you need when you're trying to implement a super X diverter, you need more space. You need physically more space in your machine to implement something that goes out to a high major radius, right? And so really you need to design your machine around possibly having some sort of super X or some sort of total flux expansion configuration. And that's expensive, having more, you know, more space. You know, every meter cube counts when you're building these things. Every meter cube adds a lot of money to the price of your machine. And so, you know, that's a decision you need to make in the early design stage, and does cost a lot of money. When it comes to something like the X diverter, though, for example, this is something that's quite easy to achieve. You know, even if you've already built a machine around using a conventional, you can still play with your colloidal field coils around your diverter to try and achieve maybe more or less colloidal flaring near the target. So, you know, configurations like these are sort of easier to achieve. And, you know, these little changes in magnetic field, not changes in how big your diverter region are, these are much easier and less expensive to achieve. But like I said, this is also limited by, you can't decrease your colloidal field too much at the target, because there's a limit on how shallow you can make the angle of intersection of your field line and your target. Yeah, if you want to know why, I can also answer, but if anyone wants to know why. But does that answer your question, Guido?
Yes, thank you.
Okay, perfect, thanks.
Thank you, Guido, for your question. I saw a question from Matthew, or a hand raised, but I don't see it anymore, so maybe I will ask a second question, and it's about ELMS, because are you working with data from ELM discharges, or is your code somehow working with loads typical from ELMS, or?
It's a good question. So currently we're just doing, you know, steady state non-ELM sort of simulations. But some of the, you know, thoughts of detachment evolution is motivated by the presence of ELMs, because the idea with detachment evolution, let's bring up maybe the polluted flared grid, is you can think about an ELM's effect on detachment as essentially changing one of your control parameters very quickly, right? It's changing the upstream power, let's say, very quickly. It's upping the power into the diverter for, you know, small periods of time, which can obviously make your plasma reattach, because we want a low power to achieve detachment. So if it spikes, you might get reattaching. So some of this work on slowing down front movement with regard to control parameter change is motivated by ELMs, because if I had, you know, my detachment front sitting in this polluted flared region or this straight down region, there would be the flared region would kind of act like a bit of a spring to sort of absorb some of the changes from the elm. So places where you have low detachment sensitivity, they could, act like a cushion for effects of changing plasma parameters, right? Because in those regions, your front is relatively stable with regards to changes in upstream conditions. Whereas, for example, if you have a straight down leg, the danger is an elm comes in, you're reattaching, and you can, not kill the target, but it's not great for the target at all. And so, the idea is if we have grids with slower front movement, those can act like a good way to cushion for something like an elm. But yeah, it's a very interesting discussion of. I mean, there are a lot of great people trying to make sure elms don't really happen or mitigate them as best as possible. But it's still good to think about, okay, if something does happen, if some plasma parameter changes, which they often do, how can we make sure that it doesn't reattach, that our plasma stays detached?
Yes, I think we share an interest about this topic and how to, because so far I read so many ways to try to deal.
Oh, I think you did. Yeah.
Maybe a combination of them could be finally meaningful for a reactor, because pellets can try to just don't have elms, also impurities to radiate it, and also the magnetic configuration in the divertor. So yeah, maybe also another question. Well, we have one from Matthew, so I will allow you, Matthew, to unmute yourself. You are able to do so.
Hey, Matthew.
Hello. Thank you very much, Cyd, for the really interesting presentation. I've learned a lot. I was wondering if you might be able to say anything about the interest of these and the increased exhaust problem and the interest in these potential solutions from the perspective of moving towards like the spherical tokamak concept. And I know that's something that's sort of being looked at in quite a lot of detail at CCFE, and how that challenge arises when you move from the conventional tokamaks that we've seen much of in sort of jet, and then the design of ITER, and then how this how the physics you've described might be more challenging in a spherical tokamak, or there might be more opportunities as well. Thank you.
Yeah. No, thanks. Yeah, that is a very interesting question, and as I'm sure you are aware, both spherical tokamaks and control of exhaust is something that CCFE is very interested in, and the mass upgrade machine is essentially a combo piece deal with both of those, right? It is going to be very challenging for spherical tokamak type reactors controlling the plasma exhaust. These are sort of generally more compact devices. You generally have less area to spread that heat fluxes, and you generally have high magnetic fields in these devices as well. And in fusion research, if you ever see talks, you'll see everyone loves high magnetic fields, apart from people who work in exhaust physics. So that can be challenging. But I will say one thing, and this is why I think this is partially why CCFE is interested in things like the Super X divertor, which we're employing in mass upgrade, is so when I talked about things like flux expansion, so a magnetic field doesn't vary linearly with your major radius. It varies with respect to 1 over your major radius. And I hope you can see that if you just have a 1 over x curve, right? If you take anywhere on that 1 over x curve and say, okay, what's the difference in your y-axis with a given step in x, right? You're going to have the biggest bang per buck at low values of x, right? So at low major radii, if you take a small step, you're changing your magnetic field quite significantly. Whereas if you go to high major radii, it falls off a lot more gently. And so something like a Super X, which takes advantage of flux expansion, can be a lot easier, or let's say more powerful, in a spherical tokamak, where your magnetic field varies very strongly given a small change in position, right? And so you don't actually have to have that much more room to have an insane, a magnetic field variation. And so that's why, for example, there can also be opportunities in spherical tokamaks. And that's why I think the UK Atomic Energy Authority was interested in the Super X, is because that can be a really powerful tool for these small, tight aspect ratio tokamaks. So thanks for the question, and I hope that answered it.
I have. Do you hear me?
Yes.
I get it. Yes. Okay.
So I have a very general question. Is the increase in the funding for fusion in the UK accompanied by an increase in the number of master and PhD students?
That's a good question. I know post PhD there are a lot of opportunities. For example, on the spherical tokamak for energy production, there have been a lot more opportunities for that since they started really increasing the funding for that. I don't know a lot of PhD projects that have opened up on the STEP reactor yet and have benefited from that increase of funding. I expect that's simply because of the stage that they're at currently, where we're trying to design this thing quite quickly, and so mainly you want sort of career employees sort of doing the dirty work there, I guess. And it's not too much wishy-washy sciencey stuff that people like me can do. So I'm not sure that the number of PhDs has increased, but for example, postdoc and research, positions of research higher than that, definitely there are a lot of great opportunities in the UK opening up because of STEP.
Okay, thank you.
And it's also a hard one because a lot of jobs are going to go away from JET over the next few years. So it might not necessarily be an increase, but simply people from JET are going to be working on STEP kind of thing rather than because there's only really a few more years of working on JET in an intense way. So.
Okay, thank you.
It's exciting but sad as well, I think.
Hello again. Thank you very much for answering my last question. That's really interesting, and your point about the diminishing returns as you sort of move away along the 1/r toroidal field curve is really interesting. Yes, I was going to ask. I think you mentioned an interesting thought about the space that's available inside a machine, particularly with regard to, I've been doodling in my little book and I've been trying to draw colloidal cross sections and fitting the whole divertor shape and particularly these large shapes inside a TF coil, and seeing how big the toroidal field coils would have to be to encapsulate these volumes. Are there challenges around sort of the proximity to the coils and the arrangements of coils? I don't know if that's an area that you've sort of looked at all, but I'd be really interested to know if you can comment on that at all. Sort of, I know that the coil arrangements in, say, mast U is quite exotic to create these divertors. I mean, no one's really tried them before, but does that pose challenges? And in particular, when you get close to a TF coil and maybe strange shapes, do they have funny effects?
As in getting close to, the big old toroidal field coils rather than the divertor manipulation colloidal.
Yeah.
I guess you can put the PF coils where you like, really.
You can, but I mean, so regarding the colloidal field coils or any coils really, I think the main issue with proximity to the plasma, especially for future devices, is shielding and insulation and things like that. I mean, devices like mast upgrades, I think, have a lot more wiggle room today. But you focus on a machine like STEP or Spark or ITER, and there's a lot of requirements for not just you have field coils and target and outer vessel. you need a lot of stuff in between. You know, you need neutron shielding, you need like you need pipes and insulation to take all that heat away. So that I'd say would be the issue with like a pollutal field coil. Getting too close to a TF coil, I'm not sure that ever happens, again, because there's actually a lot of I was about to say junk. It's far from junk, but there's a lot of stuff you have to put in between your first wall and, you know, your toroidal field coil. You're never going to get too close to it because there's actually a lot of stuff that you need to fit in between. But certainly for my work, I'm a bit more, you know, on the theoretical simulation side. So in my head, I just think, you know, magnetic field is 1/r no matter what. But I'm sure, you know, as you get closer to the edges, that approximation is not exactly true, right? We just take 1/r as an approximation for how it looks. But if you ask me how it actually looks, I don't know.
Yeah.
I'm a bit of a, you know, everything is a sphere kind of physicist.
That's great.
So,
Thank you. Thanks very much.
No worries. Thank you for your question.